In standard energy generation models, the physical vacuum is treated as a passive, three-dimensional Euclidean continuum. It is modeled as an empty stage where thermodynamic reactions simply occur. Operating within this rigid three-dimensional framework comes with a strict mathematical penalty. The conversion of mass into energy inherently produces thermodynamic entropy as an unavoidable byproduct. The infinite fractal descent, or IFD framework, approaches the local vacuum differently. Instead of a null backdrop, spacetime is conceptualized as an active, self-updating informational field, a computational substrate. This substrate is driven by a discrete temporal processing mechanism known as the recursive universal algorithm. It constantly recalculates and reloads with new inputs, computing reality layer by layer based on the iteration density within a specific volume of space. If the fabric of reality operates through discrete, computable increments rather than continuous space, its geometric rules can be actively manipulated. We can rewrite the local conditions to bypass classical entropic limits. To exploit this computational geometry, the IFD reactor is designed to induce what is known as a localized scale shift event, directly altering the local manifold. The system forces the internal vacuum away from standard 3D space, driving toward a fractional Hausdorff dimension of exactly pi. This boundary establishes the octave break-even point. At this dimension, recaptured energy equals radiative losses, converting the manifold's topological tension directly into usable energy. Achieving the octave break-even point means we are no longer constrained by the consumption of physical fuel. The reactor instead harvests the structural tension of model. Time is constructed from discrete Planck-scale causal updates. Each of these sequential updates is defined as a universal tick. The rate of these ticks establishes the fundamental clock speed of the local spacetime manifold. To access descending fractal scales, the reactor mechanism must achieve a state called phase closure. Phase closure demands that the internal resonance frequency of the contained plasma locks precisely onto the cadence of the universal tick. Without this exact temporal synchronization to the substrate's intrinsic clock speed, physical entry into deeper algorithmic layers cannot be achieved. In standard Euclidean geometry, transformations rely on Euler's formula, but in a scale-invariant vacuum, the foundational axis of recursive growth is governed by the golden ratio, phi. Integrating the growth factor phi yields the topological scaling operator, 0.4812. This defines the tension separating macroscopic gravity from microscopic recursive layers. Substituting this scaling operator predicts the exact pi boundary for the target Hausdorff dimension. Pre-calculating these eigenvalues gives engineers the precise frequency target required to tune the reactor's magnetic lattice. Translating these targets into physical confinement exposes the limits of standard fusion reactors. The smooth toroidal magnetic fields utilized in tokamaks cannot maintain structural integrity within fractional dimensions. This schematic details the physical containment solution, the Sierpinski tetrahedron coil array. It relies on a multi-scale magnetic lattice composed of nested fractal microcoils.
These microcoils project a descending gradient of magnetic mirrors, weaving a complex multi-scale boundary layer designed to hold the plasma steady. Once the internal field achieves a critical iteration density within a single Planck volume, the topological tension of the folded vacuum becomes strong enough to overwhelm the strong nuclear force. Watch how the standard atomic structures react. Instead of breaking apart, the high-energy particles collapse inward, folding into stable, interlocking topological knots known as hopfions. Forcing matter into these knotted hopfion states prevents kinetic and radiative energy from rapidly diffusing. The system recycles that energy back into the core, artificially elevating the localized dimension until it hits the break-even threshold. This process introduces the causal budget framework. Every physical system spends a finite energy budget per tick, divided entirely between two actions, spatial translation and structural maintenance. Standard atomic mass consumes massive thermodynamic resources simply to maintain its macroscopic Euclidean form against natural decay. The IFD acts as an open topological pump. By stabilizing the particles as hopfions, the reactor eliminates the maintenance cost of standard atomic forms and entirely reroutes that budget into pure topological translation energy.
This chart illustrates the recursive loop at work. The entropic waste generated at one iteration scale is trapped by the magnetic lattice and forcefully injected as the raw informational input for the next descending scale. By utilizing the universe's geometric layers as an informational recycling mechanism, the reactor achieves a mathematically negative localized entropy. Because the scale shift event harvests thermodynamic tension across multiple descending layers simultaneously, the total energy yield is highly nonlinear. The exact aggregated topological energy extraction is calculated using the phi-pi scaling factor, derived from the golden ratio to the power of pi. When equipped with fissile catalysts, the reactor yields an effective energy density of 2.36 times 10 to the 17th joules per kilogram, yielding 5 times more usable energy than current fissile systems, demonstrates the efficiency of harvesting topological geometry over standard mass-to-energy conversion. The physical shearing forces generated by this process present a severe operational risk. Unchecked dimensional tuning can lead to a state of infinite descent, causing localized tearing in the manifold. As seen in this visualization, this risk stems from an irreducible phase drift. The vacuum operates as a continuous logarithmic spiral, but the reactor's physical hardware is bound by a rigid integer lattice. Over time, these two systems drift out of alignment. To counter this, the reactor utilizes universal Tek synchronization. This protocol actively monitors the internal resonance against a strict safety metric known as the Inesca constant. If the system registers an unrecoverable phase drift, the iteration break protocol engages. The chamber is instantly flooded with Euclidean noise, collapsing the fractional dimension back to stable 3D space and safely dissipating the built-up tension as thermal radiation. The IFD reactor transitions engineering from the consumption of finite physical mass to the extraction of energy from the recursive geometry of the manifold.